So this will be equal to 5 power 3 times 600 power minus 9 divided by 133.75 power minus 9 divided by 0.02. So it's equal to 11.214 times 10 to the power 6 Pascal. Okay. So now we want to look at point B. Okay, we're going to look at point B and then we'll go to point A. So if we look at point B now, right, we look at point B. Oops. Wait, there's something wrong with my computer again. Sometimes it's the user. Yeah, you guys are seeing weird stuff. Okay. So now, again, let me draw the centroid. Right, so this is our centroid. So we're going to look at the stresses for point A. Sorry, for point B. Okay, so we are going to draw the shear flow. Right. So point A is exactly down here. So if I zoom in, right, or I enlarge this region, right. So if I were to enlarge the region, right, so you have this L thing, right, and over here is your point. No, not here. Over here is your point B, and the fact that these are all your Q's. Okay. Okay, so these are your Q. So at this location, where is point B, where I draw the dot, the area to consider is this area. Okay. Right, this area. Some of you might say, Eugene, why only that area? If I were to take a point, okay, where I'm drawing now, I'm going to take a point somewhere over here called alpha. This is the area that you consider, right? So same thing, right? So that is the area. So the area is how the area expand is relative to the what? To the shear force axis. Yes or no? So this is which I usually draw in orange. This is our shear force axis. Okay, shear force axis. Right. So that's why that is the area that we have to consider. Okay. So the shear stress at point B, right? So Q of point B. So the width is 1 millimeter, right? So that's the width. The depth is 2 millimeters, and then the Y bar is going to be what? The Y bar is going to be 24. Okay, the Y bar. Wait, is it 24? The Y bar, like the one before, is 25. Sorry. Okay. Oh, no, if it's that is the area, yeah, it is going to be 24, 25. Yeah, 25. Okay. So 1 times 2 times 25 is equal to 50 millimeter cube, or 50 times 10 to the power minus 9 meter cube. All right. So this is width, depth, Y bar. So the shear stress at point B, so V is 5 times 10 to the power 3. y bar is 50 times 10 to the power minus 9. And then we have our I, which is 133.76 times 10 to the power minus 9. And thickness, and it's just 1Q, okay, it's not 2Q. So 5 power 3, 50 power minus 9 divided by 133.76 power minus 9 divided by 2 power minus 3. So it's equal to 934.51 times 10 to the power 3 Pascal, right? So if we compare to tau max, right? When we compare to the tau max, so the maximum shear stress that we have at point D, right? We calculated just now, it was at, if I were to go back, right, at point D, it was 21.981. So if we take 21.981 times 10 to the power 6, right, and this is 934.51 times 10 to the power 3, times by 100%, right? So 934.51 power 3 divided by 21.981 power 6 times by 100. So this value is just at 4.25%. Okay, so what I'm trying to say is very small. Okay, so 934.5 power 3 divided by 21.981 power 6, right? So it's 4.25%. So it's very, very small. So you can assume that the shear stress at point B is close to what? 0. Okay, it is very insignificant. Okay, so yeah, so some calculations immediately say that it's 0. Okay, so it has some value, but it's relatively small. If you look at the solution manual, okay, so I did post the solution, the shear stress at B, they immediately call it 0. There is some value. What I'm trying to tell you is this: there is some value, but it is small. Okay, it is small. So right, and then the last one, okay, we want to find the shear stress. Okay, we want to find the shear stress at point A, right? So shear stress at point A again is quite interesting, right? Shear stress at point A. So what we consider, okay, let me get the image again. Yeah, I'll draw for you. Right, so we want to find at the shear stress at point A now, okay? So again, I draw the centroid. So this is the shear stress. Now this is the centroid. So we want to find the shear stress at point A, right? So if we construct, you can either deal with the top or deal with the bottom. Does not really matter. The answer has to be the same though. Okay, so if we were to construct the shear flow, right, moves backwards. Right, and then I'm going to have the so the line I've just drawn, that is considered the shear force axis, right? So what is the area to consider, right? So this one is pretty obvious. So the area to consider is this area over here, right? So if we look from the top, it is this or from the you can also look from the bottom, you can also consider this area. Okay. Okay, so you just need to consider this area over here. So you have to stop here. Now, some of you were asked, do I need to consider the yellow section? And the reason why it is no, right? You don't need to do that because the area, the growth of the area, okay, is from the what? Shear flow. So if we look at, so if we look at point E again, okay, let's look at this. To go to point E, right? If I have a slider, okay, so it was, I move the slider here, 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 and here. So this is how the shear flow will move, right? It will reach out to point E. Likewise, if you want to consider point A, you move your slider, right? So initially your slider is here, here, and then it stops here, right? So this is it covers the area already, right? At point E, right? So this is the slider is moving this way, so it's like this way, right? So for point A, you only consider that section, right? It's because how the area has been covered. It's not the effect of the reverse flow, right? Whereas point D has the impact of the reverse flow. Okay, point A, there's no reverse flow effect. I know it sounds a bit confusing for now, but I think you have to watch this again. Okay, then you can capture what I'm trying to tell you. Okay. So with that, you're going to look at Q. So the width is 2 millimeters. The depth, okay, the depth is, so this is if we look at this is 51. So sorry, this is the entire area, right? So this whole thing is up to here is so 50 plus 1, so it's 50. Sorry, it's not 51. Sorry, it's 25. Sorry, the area I got it wrong. The area to consider is only up to here. Okay. Okay. So if there is 50, right? So here to here is 1 millimeter, so it's 24. So this is 24 divided by 2. Okay. So 2 times 24 times 24 divided by 2 is equal to 576 times 10 to the power minus 9 millimeter, or 576 millimeter cube, or 576 times 10 to the power minus 9 meter cube. Okay. Then from here, your shear stress at point A, so 5 times 10 to the power 3, right? So V and I are constant. So this is 133.76 times 10 to the power minus 9, right? So is your Q and divide by your I. Okay. Power minus 9 divided by 133.76 power minus 9 divided by 2 power minus 3 is equal to 10.766 times 10 to the power 6 Pascal. Okay. So this problem is, if you were to ask me, I would say that this problem is the most difficult question, okay, for this thin wall. Okay, you have to get the concept right, or not it's really difficult. Okay, any questions so far? Dajinder and John, you all want me to repeat anything, or you're okay for now?
I don't really understand. Why wouldn't you? Why don't we also consider the area from B to C for A?
For A, you don't consider that. Okay, look, when I show you C, okay, right, I'm going to show you how the area is covered with time. Okay, so this So what I'm going to draw is the slider, okay? So this is time equal to not equal to 0. And then the slider move to here.